Good day everyone and welcome to my channel today. If you have not subscribed to the channel, please take a moment to do so before we proceed. This is the first video about General Mathematics, MTH 101 General Mathematics 1, and the first week we will consider fundamentals of set theory. And the entire study is in line with the core curriculum minimum academic standard developed by the National Universities Commission, which is a new curriculum developed by NUC for undergraduate students in Nigeria. I, the presenter, am Shuaibu Muawiyah Salenkano, a physicist. Today being November 23rd, 2025. Okay, here are the things we will study in this video. Foundations of set theory. And in the foundations of set theory, we have things to study today. The first one is introduction to set, then types of set, then subset, power set, and equal set. Set operations. Under set operations, we will consider only two today: union and intersection of set. Then we will consider complement of a set, and finally explain with examples the cardinality of a set. Here are our learning outcomes, what you should be able to do at the end of this lesson. By the end of this lesson, you should be able to, number one, define a set and use appropriate notation. Secondly, you should also be able to identify different types of set. Third, you should find the union and intersection of set. Fourth, determine subset, power set, and equal set. Number five, find the complement of a set. And number six, find the cardinality of a set. By the end of this video, you should be able to do these 6 activities. Now let us give it a start. The first thing, according to our objective, is to define set. Now, what is a set? Here is the meaning of a set in mathematics. A set is a well-defined collection of distinct objects. Well defined because if you look at the materials collected, you can give it a name. You can give a name to all the materials. And then they say distinct object. Distinct means they are different. Each one is different from the other, but when you take them as a group, as a collection, you can give a name to them. Examples. Here we have examples. Set of even numbers. These numbers are even numbers: 2, 4, 6, 8. You can see that each number is different from the other. 2 is different from 4. 4 is different from 6. 6 is different from 8. But when you consider them as a collection, you can see that they are all even numbers. You can give it a name, set of even numbers, even though they are distinct, different from each other. The next example is set of vowels. You see, A is different from E, E is different from I is different from O is different from U. They are 5 different letters, but when you bring them together, you will see something. What is that thing? They are all vowels. They are all vowels, so you can give it a name, set of vowels. That is what set is all about. Look at this set. You have materials inside the set. You have banana, you have apple. I don't know these two, but I'm pretty sure they are all fruit. So when you look at the materials inside, each one is different from the other. This one is different from this. This one is different from this. This one is different from this. But when you consider them as a collection, you can give a name to them. And that name is set of fruit, because they are all fruit. All of them are fruit. Now, how do we write set? What are the symbols that we use to denote set? And that is what we mean by set notation. Now, we have different ways of giving notation for set. The first one is element in curly braces. Now, this is the general name for the set. A, we can call this set A, and set A has this element. Every material inside the set is called elements. So this set has 3 elements. 1 is an element, 2 is an element, 3 is an element, and they are all enclosed in curly bracket. This is the only type of bracket you are allowed to use in set notation. You cannot use a square bracket or a parenthesis. It is not a set when you use those types of bracket. Curly braces are the only ones used. Okay. Then when you use notation in this way, we call it roster method. Then we have another way of notation for the set, and that one is a set builder notation. Set builder notation describes properties. For example, we have set B is a set of X such that X is an even number. What is happening here is that you give the variable and then you give the condition that the variable satisfies in order to be a member of that set. So in set builder notation, you do not mention the element at all. You don't give any element. You only give a variable such as X or Y or Z or any letter, and then you make the next one. Then you use this line, okay, and then after that you mention a condition that the variable must satisfy in order to be a member of the set. So the variable is mentioned and then the condition is also mentioned. From there, anyone who sees the variable and the condition can list the element of the set. So we call this set builder notation. In this one, you don't have to mention the element of the set. Then we also have membership. When we write something like this, we mean A. This A is a set, meaning set A, and that this 3 is an element of set A. This is how it is read. It means 3 is an element of A. When we cross this symbol, we mean not an element of. So in this one, we mean 4 is not an element of set A. 4 is not an element of set A, and this one means 3 is an element of set A. Now the set builder notation. What is the meaning of the set builder notation? The set builder notation is a mathematical notation for describing a set by stating the properties that its members must satisfy, meaning the condition that the member of the set must satisfy. And here is the format. The format says, you see, you have the curly braces as usual, and then you mention the variable first, then you put this vertical line, and then you mention the condition that the variable must satisfy. Okay, and this is how it is read. It is read as the set of all, then you mention the variable. For example, if the variable is X, then you say the set of all X, such that, then you mention such that, after such that, then you mention the condition. So the set of all X such that, then you mention the condition that X must satisfy in order to be a member of the set. Like if you go back a bit, you see this is from here, you can see X, this is the variable, and this is the condition that the variable must satisfy, that X is an even number. Okay. Examples of set builder notation. So we will see examples here. Here we have A is equal to, then we open the curly bracket, and then we mention the variable. Here is the variable. Our variable is X. Then we mention this line, okay, this vertical line. Then we write the conditions. You can have more than one condition, okay? And remember this symbol is an element of, we did it before. Where is it here? Here that we say 3 is an element of set A. So we have the variable here, and it says this variable is an element of the set of natural numbers. Okay, that's what this means. Natural numbers are counting numbers: 1, 2, 3, 4, 5. These numbers, we call them natural numbers, the numbers you use in counting. They are not decimal numbers, they are not negative numbers, and 0 is not included. Okay, because you don't count from 0, you count from 1, right? So 1, 2, 3, 4. It means the first condition that our set must satisfy is that it has to be a counting number. Okay, the second condition is that it should be less than 5. So what are the numbers that satisfy this condition? You see, so when you are mentioning the element, you start from 1. 1 is a natural number, is less than 5. 2 is a natural number and is less than 5. 3 is a natural number and is less than 5. 4 is a natural number and is less than 5. And these are the only elements that satisfy the conditions, the two conditions mentioned. So it means set A has 4 elements: 1, 2, 3, 4, and you can combine this using the set builder notation without necessarily mentioning the element. The second example, you see, it said B is a set of X. You see, X is the variable, and then again 2 conditions are given. The first condition says that X is a member of, or is an element of, integers. Integers are whole numbers. They can be positive whole numbers, they can be negative whole numbers, and 0 is included. You see, so it means the first condition is that my X has to be a whole number, and the second condition is that it should be less than or equal to 3. You see, 3 is included here. Here it says less than 5, so 5 is not included. But here they say less than or equal to 3, so 3 is included. Now, this means all the negative numbers are members of this set. This is why they say and so on, because here you can have -3, -4, -5, and without end to that. Okay, it goes on and on infinitely. This is why they say and so on, and then -2, -1, 0, 1, 2, 3. So they stop at 3 because the second condition says less than or equal to 3. So you cannot go beyond 3. So all these are members of the set. The third example here says C, the set C is a set of X such that X is an element of the set of real numbers. Okay, real numbers, all numbers that are not imaginary numbers. They can be decimal numbers, okay, they can be whole numbers. Any number that is not imaginary is a real number. So it belongs to a set of real numbers. All these integers and natural numbers, they are all real numbers. Okay, the next condition says that X is greater than or equal to -1. Okay, so this means set C is a set of all real numbers from -1 to infinity. There is no end to that set. So this is all about set builder notation. Oh, we got more examples. Here are more set builder examples. Okay, here is set E. Set E is a set of X such that X is an element of integer. Okay, Z is integer. The second condition here is -2 is less than or equal to my X, meaning my X is greater than or equal to -2. So it has to start from -2 and then it has to stop at -2. at 2, sorry. So minus 2 and 2 are included. So this means I have to start from minus 2 and then minus 1, 0, 1, 2, and then I will stop. And remember, these are set of integers. They are whole numbers. Any decimal number is excluded. We don't include decimal numbers. Okay. Then the next example is set F. Set F is a set of integer or variable x such that x belongs to a set of natural numbers. We remember natural numbers are counting numbers starting from 1, the numbers we use for counting. The first condition says that our variable must be a set of natural numbers. The second condition says that it has to be even number. Okay, x is an even number, meaning a number that is divisible by 2. And the third condition says it should be less than 10. So 1 must not be included because of course 1 is a natural number, but it's not even though it is less than 10, but it doesn't satisfy the second condition, so we must not include 1. Then we include 2. 2 is natural number, is less than 10, is also even, so we include only even numbers that are less than 10, and those numbers are 2, 4, 6, 8. So set F has 4 elements, 2, 4, 6, 8, according to the set builder notation. Then we have set G. Set G is a set of variable x such that x is an element of real numbers. Okay, and it is between 0 is less than x, meaning x is greater than 0, but is less than or equal to 5. Okay, so it's between 0 and 5, but 0 is not included. Since they say real number includes the natural numbers, the integers, the decimal numbers, all of them. And you can see that they are infinite. Okay, between 0 and 5, you have infinite real numbers. So we cannot mention all the elements. We can also give a name and say all real numbers greater than 0 and less than or equal to 5. Good. Now we can see types of set. The first type is the empty set, where you have no element at all. You can see there are 2 ways of denoting the empty set. You can write the curly bracket without any element inside, or you can just write this symbol. Okay, either this or this, anyone you use is correct, and it means empty set, a set without a single element in it. And then we have finite set. Finite set. A finite set is a set with limited number of elements. As you can see, this one has 1, 2, 3 elements. Okay, the elements are limited. You can count them all. 1, 2, 3. But when the elements are infinite, there is no end to the element in the set. Then we call it infinite set. This one finite set, and this one infinite set. You can see 1, 2, 3, and so on, meaning there is no end to it. Then we also have universal set. This contains all elements under consideration. All the elements under consideration, like if I am considering a set of the letters I have, the A, B, C, D from A to Z, then that makes universal set. If I am considering a set of all integers from 1 to 100, and from there I can extract more set from that, then the integers that I have from 1 to 100 is called universal set. Then we have subset. What do we mean by subset? Set A is a subset of B if every element of A is in B. Meaning, if I have a set A such that every element of this set A is obtained from set B, then set A is a subset of B is like a mini set. Okay, you extracted this set from this set B. You extracted set A from set B. Now, how do we show that in set notation? This is how it is written. Okay, and it's read: A is a subset of B. A is a subset of B, meaning all the elements of A are found in B or are obtained in set B. Example, set A has this element 1 and 2, and set B has this element 1, 2, 3, 4. You can see that all the elements of set A are obtained in B. 1, 2 are also found here, 1, 2. So we can conclude that set A is a subset of B. Okay, it's a subset of B. Then there is what we call proper subset. Proper subset. And what is the meaning of proper subset? A set A is a proper subset of B if it has fulfilled these two conditions. The first condition is that every element of A is in B. Okay, that's necessary to make it a subset. Okay, so that A is a subset of B. The second condition is that A is not equal to B, meaning A is not equal to B. They are not equal set. Okay, if we want them to be proper set, then they must not be equal, meaning if B also has 1 and 2 only as its element, meaning in set B you don't have 3, you don't have 4, you only have 1 and 2, just like A, then A is not a proper subset. This means that for A to be proper subset of B, B must have all the elements of A and one or more additional elements that A does not have. Okay, when this happens, we say A is a proper subset. Proper subset continues. This means B contains all elements of A plus at least one more element. Here are examples. You see, in this example, you have A is a set of 1, 2. It has this element 1 and 2, and B has 1, 2, 3, 4. Okay, so you can see that at least after 1 and 2, B has 2 extra elements that A does not have. So A is a proper subset of B. We can write this and say A is a proper subset of B. Okay, more examples. C is a set of A and B, meaning it has A and B as its element, and then D has this element A, B, C, D, E. You can see that this D has A and B. A and B are also its element, but in addition to that, it has C, D, and E that C has not in its set. Okay, so we can conclude that C is a proper subset of D. Again, E is a set of 2, 4, and 6, and F is a set of 2, 4, 6 with additional element 8 and 10 that E does not have. So we can conclude again that E is a proper subset of F. Okay, now look at the third example here. G is a set of 1, 2, 3. H is a set of 1, 2, 3. We cannot say that G is a proper subset of H because they are equal set. They are equal set. This is impossible. At least H should have one more element that G does not have to make this proper subset. Otherwise, of course, we can agree that G is a subset of H, but not a proper subset because they are equal set. More proper subset examples. Okay, look at this one. I is a set of cat and dog. J is a set of cat, dog, bird, and fish. So I is a proper subset of J because J has additional element bird, and fish that I does not have. Then we can use set builder notation also for that. Look at this. K is a set of x such that x is an element of natural number and is less than 5. Okay, so this means K, remember natural numbers are counting numbers. So it's if K has element such that the element is in natural number and is less than 5, then it starts from 1 to 4. 1, 2, 3, 4. 1 is a natural number and is less than 5. So is 2, so is 3, so is 4. Okay, and then L. So with that we mention the element of K. Then look at this one. It says L is a set of x such that x also belongs to natural number and x is less than 10. So x starts from 1 to 9. You see, all the way to 9. Now, by comparing the element of K and L, you can see that all the elements of K are found in L. And L has extra elements, so K is a proper subset of L. Now here is one more thing that is interesting. M is an empty set, okay, but N is a set of 1, 2, and 3. It has element, but M has no element. We can say that M is a proper subset of N. This is because empty set is a proper subset of any non-empty set. Okay, any non-empty set, empty set is a proper subset of it. Okay, proper subset versus subset. How do you differentiate? If it is just subset, you can use this symbol, and that means, for example, A is a subset of B, means A is contained in B. All the elements of A are in B, and using this symbol you are allowed to say that A is equal to B. Is allowed. It's possible that all elements of A are in B and all elements of B are in A. Okay, they can be equal set. But proper subset agrees with the first one that A is a proper subset of B, means A is contained in B, but A is not equal to B, meaning they are not equal. Does not allow A to be equal to B. This symbol does not allow set A to be equal to set B at all, and that is the difference between the two. When you use this one, always remember that the two sets are not equal at all. But when you use this one, it's open. They can be equal, they can be non-equal. We have examples to illustrate that. Look at the first one. This set has two elements, 1 and 2, and the second set has these 3 elements, 1, 2, 3. You can write this and say, okay, this set is a subset of this one, and that's correct. And you can also say that this set, same as this, is a proper subset of this, and that's correct. Because why am I right? Okay, let's take the first one. Why do I say that this set is a subset of this? Because all the elements in this set are found here. 1, 2 are found here. So this condition is satisfied. Once this condition is satisfied, I am allowed to write this symbol. Okay, but the second condition here, the second one here, two conditions must be satisfied. Number one, all the elements here must be found here. Number two, they must not be equal. And you can see that all the elements here are found here. So first condition is satisfied. Second condition, they are not equal, because this set has at least 3 here, this element 3, that is not contained in the first one. So you can write this. Secondly, thirdly, look at the two sets here. This set are equal. All the elements that are found here are also found here. This condition is enough for me to write this symbol and say this is a subset of this, but I will not write this one. Okay, even though all the elements of this set are found here, but they are equal set. This one has to contain at least one extra element that is not found in here before I can write this symbol. And because they are equal set, I must not write this symbol. Okay, I hope that is understood. Now the next thing we will consider is equal sets. What are equal sets? Two sets A and B are equal if they have exactly the same element, meaning all the elements of A are the same element you will find in B. All the elements of B are the same element you will find in A. Then the set are said to be equal. Here is the notation. The notation is written set A equals set B, and this means set A is a subset of B and set B is also a subset of A. For example, set A is a set of 1, 2, 3. These are the elements, and set B is a set of 3, 2, 1. These are its elements. You can see that the way elements A are arranged is different from the way elements B are arranged, but it does not matter. What matters is that all elements in A are the same element you will find in B, so set A is equal to set B. They are equal set. The next thing is power set. What do we mean by power set? The power set of set A, for example, is if A is a set, then the power set of this set A is the set of all possible subsets of A. Remember, a subset is a set that is extracted from a given set. Okay, it means from this set, how many small sets can you extract out of this? And this number is what we call power set. This set, when you extract, for example, 5 sets, and then you also form a set of those sets, now this large set is what we call power set. The power set of set A is the set of all possible subsets of A, and this is how it is denoted in notation, and this is read the power set of A, the power set of A, or you say the power set of set A. And there is a formula for getting the number of elements in your power set, and the formula says if a set has n elements, like this set A, let's say it has n elements, where n is the number of elements. If A has 5 elements, then n is 5. If A has 6 elements, then n is 6. Okay, its power set has 2 raised to the power of n elements. We will see that in example how it is used. Okay, for example, let's say set A has this element A, B. So you see it has 2 elements, so it has n is equal to 2 elements. So the power set is a set of all the subset, all small sets that you can obtain from set A. When you combine them to form a set, that set is the power set of A. For example, the first one is I can have an empty set. Okay, an empty set is a subset of any given non-empty set, so we have to start with that. Then we can have a set that has only A in it. Can you see? Secondly, we can have a set that has B only, and lastly we can have a set that has all the elements. So this set is called the power set, and you can see that it has this 1, 2, 3, 4 set. Okay, it's a collection of 4 sets, and to know the number of elements in it, you just have to say 2 raised to the power of n, and your n is 2, so 2 raised to the power of 2 is 4. So your power set will have 4 elements, and we can see the element 1, 2, 3, 4. That's the meaning. Then what do we mean by union of sets? The union of sets A and B. Let's say I have set A and I have set B, and I want to get their union. Is the set of elements in A or B or both, meaning this set will have elements that are contained in A or elements that are contained in B or all of them. And this is how it is written. It's like uniting all the elements of A and B together without repetition, meaning if A has a particular element and that element appears in B, you write that element once. You don't repeat it twice just because it appears in both. You write only one. And in notation, this is how it is written, and it's read A union B, A union B. For example, A is a set of 1, 2, 3, and then B is a set of 3, 4, 5. Now, if I want to get A union B, it will be a set of 1. You see, I have this, so I write it. 2 appears here, so I write it. 3 appears here and it appears here. I will write only 1 without repetition. Then last, I have finished with A, so I go to B. I have written this already, so I then include my 4 and my 5. So going back to the definition, you can see that the definition says that the union of A and B is the set of elements that are in A or B or both. The elements that are in A, you can see 1, 2 are all in A. The elements that are in B, 4, 5 are in B. You don't find them in A. And the elements that are in both of them have 3. You see 3, 3, 2. So you combine all of them together. That is called union or set. What about intersection? Intersection of set. The intersection of set A and B is the set of elements common to both, meaning the elements that are found in A, they are also found in B. These are the only elements you consider, and we call that intersection. And in notation, in set notation, this is how it is written, and is read A intersection B. A intersection B. Here is an example. Set A has element 1, 2, 3. Set B has element 3, 4, 5. Now the elements they have in common is 3. You have 3 here, you have 3 here. 1 is here, is not here. 2 is here, is not here. 3 is here, is not here. 5 is here, is not here. The only element they have in common is 3. So you can say that A intersection B is a set of a single element 3. Okay, let's see what we have next. Complement of a set. What is the meaning of complement of a set? Now, the complement of set A, let's say A is a set. So the complement of set A is the set of elements in the universal set that are not in A. Okay, suppose this A, if you have a universal set, then all the elements in set A are in that universal set. Now, if you want to find the complement of A, it will be a set of all the elements that are not in A, but they are found in the universal set. In notation, you can either write it like this, A prime, or you say A raised to the power of C, but it's not written it's not read A prime or A raised to the power of C or by A. If you write this symbol or this symbol or this symbol, any one of these 3 is read complement of A, or you simply say A complement, A complement, A complement. This is how it is read. The first 2 symbols are more common. This one and this one, these 2 are more common. Okay. And here is the formula. A complement equals universal set minus set A. So you extract all the elements that are in A, you cancel them, and you leave only elements in the universal set that are not in A, where this symbol is their universal set. Okay, here are some examples. My universal set is a set of numbers from 1 to 10, natural numbers, counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And A is a set of numbers 1, 3, 5, 7, 9. You can see they are odd numbers, right? So A complement will be elements that are not in A but are found here. So 1 is here, I don't take it. 2 is not here, I take it. 3 is here, I don't take it. 4 is not here, so I take it. And then 5 is here, I don't take it. 6 is not there, so I take it. 7 is here, I don't take it. 8 is not there, so I take it. 9 is here, I don't take it, but 10 is not there, so I have the set. And the set, remember, set is collection of well-defined objects, right? So you can see that this set are all even numbers, so all even numbers from 1 to 10. Example 2, let's say my U is a set of letters, okay, A, B, C, D, E, F, G, I, O, U, and then B is a set of vowels extracted from here, A, you see, and then E, I, O, and U, okay. Then B complement will be a set of elements that are not in this B, but they are in the universal set. A is there, I don't take it. B is not in here, so I take it. C is not here, so I take it. D is also not here, so I take it. But E is here, I don't take it. F is not here, so I take F. G is not here, so I take G. But I, O, U are all here. I, O, U, I don't take them. So my B is all consonant in the universal set. Okay. More complement examples. For example, if we say, for example, that your universal set is a set of all students in class, all the students in the class, then set C is a set of students who like mathematics, and definitely not all students like mathematics, right? So if C is a set of all students who like mathematics, then C complement should be a set of students who do not like mathematics. That is C complement. Then another example is if you are U, if this set U is a set of all integers, and then remember integers are whole numbers, right? Okay. Then D is a set of all even integers, integers that are divisible by 2, such as 2, 4, 6, 8, 10, and so on. Then D complement should be odd integers, right? Because integers can either be even or odd. So if D is a set of even integers, then its complement should be a set of odd integers. I hope you understand that. Okay, here are a few examples before we move on. Example 1 says, let A be a set of 1, 2, 3, 4, 4 elements, and then B is a set of 3, 4, 5, and 6 elements. Then we should find A union B, and then 2, A intersection B. Here we are uniting the element of A and B, and here we are finding the elements that are found in A and B only. And then lastly, they say we should show that this set that has 2 elements, 1 and 2, is a subset of A. Remember, when you remove this line, it becomes proper subset, right? But if you don't remove it, you put this symbol with this line, it means this set is a subset of A. Okay, we should be able to show that. Okay, let's do this. The first thing is we are going to write all the set we are given. We are given set A with this element, we are given set B with this element. Now, number one thing that they say we should do is to find the union of A and B. Okay, it means we are combining this, and remember, if any one of them appears in both, we are writing that once. So let's start with A. We put this one, then we put this 2. 3 also appears twice, but we are writing it once. 4 also appears twice, but we write it once. Okay, after that we have written this. So 5, 6. So we included this. This is our A union B. Then A intersection B should be a set of elements that are found in A and also in B, and we have only two elements like that. We have 3 and 4, so it will have set of two elements, 3 and 4. Now the last one is, of course, we have to agree that this one is a subset of A. Why? We give the reason in bracket. All the elements of this set are in A. It has this element 1 and 2, and do we find them? Yeah, 1 and 2. You see, they are all in A, so this is true, of course. Here is the second example. Find the power set of C is equal to X, a set of X, Y, Z. Okay, meaning C has 3 elements in it. X is an element, Y is an element, Z is an element. Then we should find the power set of this. How many subsets does it have? Okay, finding the power set, meaning we have to collect all the sets, all the subsets of C in a set, and let's do this. Look at it here. C is a set of X, Y, Z. It has n equals 3 elements. How many elements? 1, 2, 3. So if you want to know the number of subsets, you use this formula. Remember the formula we gave? Where is this formula when we were explaining the power set? Well, you see, 2 raised to the power of n, where this n is the number of elements. Okay, n is the number of elements. Let's go down and see. Great. So 2 raised to the power of n, my n is 3. So this is 2 raised to the power of 3, and 2 raised to the power of 3 is 8. Remember, 2 raised to the power of 3 does not mean 2 times 3, because 2 times 3 should give you 6. So it means 2 times 2 times 2, and that will be 8. Okay. Okay. Now, how many subsets can you get from here? You can get 8 subsets. Okay. You should always remember that the first subset is the empty set. You see. Okay, the first one is the empty set, and the second one is a set that has only one element, X. The third one has Y only, then Z only. Then you combine X and Y, and then you combine X and Z. You see, then you combine Y and Z. You see, and lastly you combine all of them. So if you count this, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 elements. Okay, and this is why the number of subset here is 8. Remember, each one here is a set. This is a set, this is a set, this is a set. Okay, and then you collect all of them also as a set, and that makes it a power set. Okay, I hope that is understood. Problem as example problems continue. So we have problem 3. Problem 3 said, given that I have this universal set, okay, a set of numbers from 1 to 10, and A is a set of even numbers 2, 4, 6, 8, 10, and B is a set of odd numbers 1, 3, 5, 7, 9. So they say we should find A complement. Remember, A complement means a set of elements that are found in the universal set but are not in A. B complement, and then A union B complement, meaning you have to unite the element of A and B, and after that you find their complement. So let's do this. Okay, the first thing, remember, is we are given our universal set, we are given set A, we are given set B. So the set of elements that are not in A, okay, remember A collects all even numbers. So if you remove all the even numbers here, you will be left with odd numbers 1, 3, okay, 5, 7, 9, okay. So this will be your A complement. and this A complement will be exactly as B, because B is a collection of all the elements that are odd, okay, odd numbers. Okay, so this is why they say is equal to B. Then B complement means you remove all B elements here. Okay, you remove them in the universal set, and what remains is your B complement. So 1 is in B, I don't take it, I take 2, I take 4, okay, I take 6, I take 8, and I take 10, and I will have exactly what I have in A. This is why they say is equal to A. Now if I unite the two, A union B will give me everything in the universal set. Can you see everything? Because you are uniting the odd numbers and the even numbers together. So you have the numbers 1 to 10 all together, and this will be exactly equal to the universal set. Now if you want to get the complement of A union B, you see open bracket, close bracket, you put this together, and you want to get the complement of this, meaning all the elements that are in A union B, but all the elements that are in the universal set, but they are not in A union B, and A union B is exactly what you have here. So there is no element in A union B that is in the universal set that is not in A union B, right? They are exactly the same. So if I say this one minus this one, I will not be left with any element, right? This is why A union B complement becomes empty. It's an empty set. Okay, it's an empty set. Then example problems continues. Okay, write in set builder notation and list the elements. Okay, the set of all integers greater than or equal to -2 and less than 3. How do we write this in set builder notation? Remember, in set builder notation, you have a variable and you also have condition. Okay, so if we have a variable, here are the conditions given. Then our x, if we take x as our variable, then x must belong to the set of integers. Okay, not only belonging to the set of integers, it has to be the second condition is that it has to be greater than or equal to -2, meaning it should start from -2. Okay, and then it goes on -2, -1, 0, but then it say it should be less than 3, so we stop at 2. So this is the set builder notation. You see, A is a set of x such that x is an element of the integer, meaning it belongs to the set of integer. Okay, that is the first condition, because they say here all integers, set of all integers, right? But the second condition say greater than or equal to -2 and less than 3. So you have to write that here, less than or equal to -2 less than or equal to x, meaning x is greater than or equal to -2. Again, x is less than 3. Okay, so if you are listing the element, you can say the element are -2, -1, 0, 1, and 2. Okay, you can also write this. To simplify this, you can just say that, okay, my x is a member of, or is an element of integer. Okay, and then you write the condition here that not only is it a member of integer or belong to the set of integer or is an element in the set of integer, it has to satisfy this, that my x here is greater than or equal to -2 and less than 3. Okay, where this symbol represents the set of integers. Okay, the next thing is cardinality of a set. What do we mean by cardinality of a set? By definition, the cardinality of a set is the number of elements in the set, okay, or just the number of elements in the set. Okay, here in notation, this is how it is written. You see, n of a, or just the absolute value of A, but it is not read like that. You just read it as the cardinality of set A. This one too, you read it as the cardinality of set A. This is how it is read in set language. Okay, both means the number of elements in set A. That is the meaning. Okay, the number of elements in set A. That is what it is meant. For infinite set, meaning if the number of elements of the set has no limit, we say that the cardinality is infinite. Okay, examples like this A has element 1, 2, 3, 4, 5. How many elements do you have? 5. So the cardinality of set A is 5. B has this element 1, 2, 3, 4, 5, 6, 7. So the cardinality of set B is 7. Remember, I said you can either use this symbol or you can use it like this. Okay. C has all these elements. If you count the number of elements you have here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the cardinality of set C is 10. Okay. Then D is an empty set, no element at all. So the cardinality of set D is 0 because it has no element. E has this 1, 2, and 2 is repeated, and then 3 again is repeated 3 times, 4 is repeated 4 times. But remember, in set, usually even if a number is repeated, we are taking that as 1. So you have 1 element here, 2, 3, 4. Only 4 elements because only distinct elements count. Okay. F here is a set of red, blue, green, yellow. So how many elements do you have? 1, 2, 3, 4. So the cardinality of F is 4. Then you have G is a set of X such that X is a vowel in English. So this is in set builder notation, right? And it has satisfied our condition. We have number of vowels is 5. You have 5 vowels in the English language, right? So the cardinality of set G should be 5. And then H is a set of all prime numbers. All prime numbers. Prime numbers are numbers that have only 2 factors, 1 and themselves. Any number that has 2 factors only, 1 and itself. Okay, like 2 is a prime number. It has 2 factors only, 2 and 1. 3 also, 3 and 1. 5, 5 and 1. Okay, but 6 is not. Okay. 7 is a prime number. 9 is not because after 9 and 1 you have 3. 3, okay, is a factor of 9. 11 is a prime number. 13 is a prime number. 15 is not because after 15 and 1 you have 3, you have 5. 17 is a prime number. If you continue like that, you find out that there is no limit to the number of prime numbers that we have. For that, the number of elements in set H is infinite. So the cardinality of set H is also infinite. So we put the infinity symbol to mean that its cardinality is infinite. Okay. Here we say cardinality with set builder notations. If you are given set builder notation and you are asked to find cardinality, how do you do that? No element is given, only the conditions. Okay, so I is a set of X such that X is an element of the natural number. Remember, natural number is the counting numbers 1, 2, 3. 0 is not of them, right? And your variable is X. The first condition is X belongs to the natural number or is an element of the natural number. And second condition says X is less than or equal to 8. This means it should be from 1 to 8. Okay, so you have 8 elements. Then the cardinality of I should be 8. Then second condition, second example, J is a set of X such that X belongs to the set of integers. Remember, integers are whole numbers. 0 is included, and you can have negative integers, you can have positive integers. And then this one gives us the range of the values of x from -3 to 3. So you can count -3, -2, -1, 0, 1, 2, 3. You have 5. Sorry, you have 7. Okay, if you count, you see that you have 7. So the cardinality of set J is 7. K is a set of x such that x belongs to natural number. That is the first condition. Second condition is that x is an even number. Okay, it's a counting number, it is even, and it is less than 15. So let's start. What's natural? So we have 2. Let's begin counting. 2, 4, 6, 8, 10, 12, 14. You see, 14. You have, it means you have 7. If you count properly, you see that you have 7 elements. So the cardinality of set K is 7. Okay, just select natural numbers that are even and less than 15. You have 7 numbers there. Okay. Wow, I didn't realize we have just completed it for the first week. Thank you for your attention. Stay tuned for week 2. Very soon I'm going to give another lecture video for week 2. Thank you for watching. Assalamu alaikum.